Type systems are a collection of rules that check the correctness of your programs, which at this point won't tell you much. So, to break it down, I'm going to start with the purpose of type systems. Type systems prevent execution errors by preventing unintended behavior like operating on wrong operands, for example, multiplying incompatible data types. They prevent invalid state like undefined results from reading out of arrays. And type systems have an additional purpose of allowing you to create interfaces, which allows modular design of your system. Type systems have one golden rule. They prefer raising an error instead of allowing unintended behavior or invalid state. Their responsibility is to inform you of problems in the code. They do not relieve you from fixing errors. The algorithm to check type correctness is called type checking. This raises the first important question. When are types checked? You will learn that type checking can be done at compile time. This is known as static type checking. You probably know that Python is a dynamically typed language. Python checks types at runtime. But with the help of type hints, you can perform static type checking in the code editor or from the command line. You will see that all these things fit into the Python language. And perhaps this is a good time to explain the second rule about type systems. There is no one type system. Type systems have various categories and each programming language is somewhere on a spectrum. There is dynamically typed versus statically typed, implicitly typed versus explicitly typed, structurally typed versus nominally typed. The Python type system has a place somewhere in these three categories, and by the time you finish this course, you have seen all of them, know what they mean, and learn their terminology so you can search online and communicate in your team effectively. You will learn that Python is dynamically, implicitly, and nominally typed. But the place on these spectrums is not a Boolean. For example, with the help of static type checkers, Python code can be statically type checked. And although Python is nominally typed, it does also support structural typing with the help of protocol classes. And there is one more property that is important to us. Regardless the place of a programming language on this spectrum, there is also the degree of how strict types are enforced by the type system. In this course, I will call this property type flexibility, and you will learn that a type system might allow you to bypass logical type constraints to allow more flexibility. As you see, it is quite a type party. So it is time to learn what all these type system properties mean. And for this, we have to start with the basic building block of any type system: types. If you are interested in a course about types, I bet you have already worked with them. You know that 3 is an integer, hello is a string, and true is a Boolean. Types tell us the kind of data of a value. But they have more purposes. A type can specify the operations that can be performed on it. For example, ints can be multiplied, strings can be made uppercase, and lists accept elements to be appended and removed from it. Ensure correct data. It will fail to put an arbitrary string in a number data type. It can group types like ints and strings in composite types like classes, and use composite types as interfaces for modular design. But let me start at the beginning and explain why types were created in the first place. Historically, the reason is a technical one. Deep down in your computer, all program code and data is stored as ones and zeros. At this level, a general-purpose computer is not able to discriminate between memory addresses and instruction codes or between text or numbers. Data types do not exist at this level. So, how is data stored without data types? Let me take you back to 1986 and start up my Commodore 64. in its memory, I want to store a number ranging from 0 to 255. Here you see the binary representations from the numbers 0 to 255. As you can see, I will need 8 bits to store such a number. The required number of bits is called the upper bound. At this point, I need to do a couple of things. Let's say I want to store the number 150. First, I have to convert it to binary. For this, I use Python. I am now ready to store this number. I pick address 2000 and store the bits. The next number I will store is 60,000. I use Python to convert it to binary. For this binary number, I need 16 bits. Since 8 bits were already taken at address 2000, I store the value at the next address, which is 2001. Notice I have to keep a list where I store my data. And not only the starting address, also the size of the data. Yes, there was a time where it was very common to keep lists of such variables in programs. But doing this manually is very dangerous. Let me show you why. I want to read the number at address 2000, but I make a mistake and instead of reading 8 bits, I read 16 bits. You can already imagine the problem that now occurs. Technically, this will work just fine, but the value will not be correct. This is a huge problem because the program won't even notice something went wrong. The same applies when the number is 16 bits, but I only read 8 bits. Instead of the number 60,000, I read the number 234. The biggest problem at this time is that the program keeps running, but the value is not correct. The system is in an invalid state. I will only find out later that there is a problem. Errors that occurred but are not spotted immediately are called untrapped errors. They are the worst kind of errors because they usually do not appear in the same place where they originally occurred. This makes debugging very hard. Untrapped errors can be the result of a mistake by the programmer, but also a result of an exploit in the system. Hackers search for weaknesses in the system all the time. Any help you can get from a type system to prevent data corruption is much appreciated. Now let me warn you, what I showed you here is a vastly simplified version of what is actually happening in a modern computer. But it does indicate why types are useful and even needed in the first place. So, instead of manually counting bits, we need an abstraction to add more safety, and thus types were invented to prevent untrapped errors. An additional benefit of types is that compilers can use them to optimize the compiled program for the available hardware. For example, the compiler can decide to use hardware floating point arithmetic when dealing with floats. Now perhaps you wonder, untrapped errors, compilers, what does all this have to do with Python? Well, it turns out that types have many more benefits, but even the ones I just mentioned are important to us when you realize that a big chunk of Python itself is written in C, a compiled language. Types play a huge role in keeping systems in a valid state. But everything you saw so far is pretty much invisible to the Python programmer. So, when are types starting to become visible for us Python developers? When Python is installed, you get access to the Python standard library. The standard library contains functionality that programmers can use to write Python programs. But where is this standard library? The Python standard library is stored in 2 places. Parts of it can be found as Python modules on your hard drive. An example of this is the datetime module. You can check this yourself with a file search. And some of the functionality is built directly into the Python interpreter. Examples are built-in functions, built-in constants, and also built-in types like ints and strings. The Python documentation provides a list of built-in functionality. In this course, we will mostly focus on built-in types. Let me start with the most easy way to use one. I assign value 10 to A and print A. There is already so much happening under the hood, and the first thing you need to know is that A is an integer. You can test this with the built-in type function. That worked. So I said that the type can be checked with the type function. But if you look at the Python documentation, you will see that type is actually a class. When it is instantiated, it takes an object, and when it is printed, it shows the type. The documentation continues to describe where it found the type. I'll inspect this attribute manually. That works as well. By getting and printing the type of A, one thing is already proved. Python is a typed language. Another interesting thing is that the object stored a reference to the class that was used to create the object. The type information is stored in the object, which is an important feature for dynamically typed languages, as you will see later. But first, let me show you a second example. I create integer A and float B. Python shows the type of both variables. This teaches us another interesting Python feature. Notice I did not annotate A and B to be of a specific type. How was Python able to understand that 10 is an integer and 4.3 is a float? Python infers the type from the assigned value. This is called implicit typing, which is one of the key features of Python. Python can infer more types, like strings, lists, and tuples. All these types were inferred without manually annotating the variables. I went through my Python code and checked which types I often use. It turns out there are not that many. Here's a list of them. I'm trying to think of more, but this is pretty much it, and I bet that you also use them in your programs. So, what do they do? Integers are used to store round numbers. They can be negative, 0, or positive. Floats are used to store fractions, small numbers, and big numbers efficiently. Booleans express things that are true or false. The first three data types are scalar data types. That means that they store a single thing. One int stores a single number. One bool stores either true or false. But now we get to the string data type. A string is a container for characters. The container can contain 0, 1, or many characters. This is known as a sequence type. And there are two other well-known sequence types, namely list and tuple, with their most important difference that a list is mutable and a tuple is not. And there is the dictionary, which allows for fast, unambiguous lookup. The dictionary type is a mapping type because it maps keys to values. The last data type in the list stores dates and times. But what kind of type is this? To answer this question, I look at the Python documentation. Look at the word attributes. It is plural. The date-time type combines scalar values for year, month, day, etc. When data types are composed of other data types, we call them composite data types. Now I can make this list complete. One thing is important to know. Once you start reading documentation of other languages than Python, you might find different names and different definitions for the kind of types. Let me give you an example. Perhaps you have heard the name primitive type to describe the scalar types you see on the screen. In languages like C or Java, primitive types are data types that just have a value, unlike types that contain one or more values and methods to operate on it. The reason to make the distinction is a technical one. These so-called primitive value types are much more efficient than objects. But that said, in Python, everything is an object and thus it has no primitive types. So I'll stick to the words scalar, sequence, mapping, and composite. And there are even more kinds of types. If you have used a set, you have used a set type. The type of a function is callable. And there is the none type. I just showed that datetime is a composite type. And how is this composite type made? You already know this because you probably used it many times. A class can be used to compose data types. Your class becomes a new data type. Let's inspect the type of a custom class. Here is class point. It takes and stores two numbers. I instantiate a point. At this point, I am not interested in the data types of x and y. Instead, I want to know the data type of instance p. As you see, the type of p is point. And that means that class point was used to instantiate object p. You already heard me saying that in Python, everything is an object. Does that mean that the point class is also an object? Well, if that is so, I must be able to print it. And I can. If you bring your experience from another language like C# or Java, this might seem strange. But in Python, when a class is defined, it will also become an object. And what is its type? Aha! A Python class is of type type. To create a composite data type, you can use classes in Python. The point class is composed of two scalar data types, x and y. Now you have seen different levels of data types. First of all, there are scalar data types. They represent a single value like a number. Then there is the composite data type, which is the point class that was used to create the instance. But even the class itself has a type. Here you see that the point class is of type type. This category is known as the kind. These categories are type abstraction levels, but they are quite theoretical in Python. And there is a simple reason for this. In Python, everything is an object. In some languages, types are not objects and the distinction in this table would be more obvious. Even classes are objects and perhaps you have seen that the data types I used can also be instantiated using their classes. Int is a class, float is a class, string is a class, and list and tuple. Yeah, you see where I'm going with this. It cannot be said enough. In Python, everything is an object. Let me demonstrate this by instantiating data types explicitly. Look at these lines. The first line creates an integer with value 10 by using an integer literal, which I will explain in the next chapter. The second line also creates an integer with value 10 by instantiating the integer class. You can do the same for common built-in types. Yes. At first sight, both methods look like they do the same, but there are important differences. By using a literal, the type is inferred. By targeting a class name like int, the resulting value will be an int, or an error. And that brings me to the second important difference. Look at the float class. The documentation says it can be constructed from a number or string. Let me test that. Now I can create a float from a float. Okay, what happens if I pass an integer? Or a string? By using the float class explicitly, the resulting type will always be a float. Well, not always. Python gives a value error. Makes sense, right? The fact that you can pass arbitrary data types to these classes will play a role in converting types, and you will see more of that in another chapter. When we talk about types, we also must talk about type errors. The first question I have is, who raises type errors when things go wrong? Look at this code. I subtract string B from string A. This results in a type error. Python says it cannot subtract strings. You might think Python takes both strings and tries to subtract them, but actually the subtraction is done by the string objects. And more precisely, it is done by the left-hand operand. Python knows the type of A. It is a string. It now searches in the string type for a method called dundersub. But dundersub is not supported in string types, and Python gives a type error with the message you see on the screen. If you ever wonder how things work in Python and the documentation does not provide the technical details, you can always look at the CPython source code on GitHub. Look at the code. There is our error message. Let me show you another example of things going wrong. This time I add a string and float. When I first tried this in Python, I was surprised. I expected this result, but in fact I got an error. Python does not allow to add strings and floats. But here is an interesting thing. I swap the operands, I execute the code again and get a different error. Why does the error message change when the operands are swapped? Well, the error is raised by the object on the left-hand side of the operator. Let me show you a few more calculations. Here are int 10 and float 3.2. Their types are not compatible, and yet I can add them. That is interesting, and it gets even stranger. Why did that work? It is interesting that Python allows me to add an int and float, but not a string and float. But then multiplying strings by integers is fine again. What all these situations have in common is that conversions are required. But since I am not doing this explicitly, Python tries to do it implicitly, and each object can specify how to implement the conversion. Or not. This behavior is sometimes colloquially described as weakly versus strongly typed, but this is an ambiguous description, as you will see in a later chapter. But first, I want to explain why and how this code works, and in the next chapter you will see the mechanics of variables in Python.